Hey guys, welcome. Yeah, so we're going to continue talking about convergence of series, and this time about the integral test. And since this is example 0 in the tradition of all example zeros, we're not only going to state the integral test here, but we're going to prove it. Yeah? Alright, first the statement. So the statement goes like this. Suppose that f of x is continuous, positive, and decreasing on some b to infinity, and that f of n is some a sub n. Then what I'm about to show you follows, but first, it's important that f of x be positive and decreasing somewhere down the road, but not necessarily at the start, yeah? Okay, cool. And so here's what follows, which is that if this integral is divergent, then so is the corresponding series. Yeah? Okay, cool. And also notice that the integral and the series start at the same place. Additionally, if the integral is convergent, this integral is convergent, then so is the corresponding series, yeah? Okay, so the proof is going to require both showing this first part, the divergence part, and the convergence part. We're going to start with the divergence part. So here goes the proof. For the proof, no, the other direction. Okay, for the proof, we need to begin with this visual. Notice that in this visual, by the way, this visual is made using GeoGebra. But yeah, in this visual, this green curve is the function f of x. And we've shown that f of x is approximated by rectangles. And since f of x is decreasing, the rectangles here will be over approximations. Yeah? Okay. And by the way, I only show a finite number of rectangles, but the rectangles are supposed to continue ad infinitum, right? Look at this, right? Okay. So where to from here? How about this? Which is clearly the area given by the rectangles, so the approximation of the area under the curve given by the rectangles looks like this. And if we want to be more explicit, then we could write this, which is that the first rectangle is 1, the base, times the height, which is f of 2. And then the next rectangle, again, 1, the base, times the height is this time f of 3, and so on. So the area approximated by the rectangles is, where's my mouse? Right here. Okay, this here. Okay, and we could then say that this is the same as this, because since we're saying f of n is some a sub n, then f of 1, since we're starting with 2, f of 2 is a2, and f of 3 is a3, and f of 4 is a4, and so on. You get it. Okay. And then, as I've already stated, since this time the rectangles over approximate the exact area. The exact area is this here, and so the exact area is less than the sum of the areas of the rectangles. That's what this says, right? Okay. And from here, how about this? Since we want our series to start at 1, what we could do is on the integral, add on f of 1, and then on the series, add a1, and then that way we can have our series start a1, and this inequality still holds, right? Okay. And then we see clearly that as k goes to infinity, f of 1 plus this integral is, since we're saying divergent, diverges, right? This goes to infinity. So then, since this here is smaller than this right-hand side, it must mean then that our series, by the way, our series is supposed to start at 1, but yeah, our series diverges, right? Okay, I've already showed that it starts at 1 here, but I'm not going to re-record this video just because of this small blunder. Okay, now let's show the other direction. For the other direction, we're going to use this visual, right? Okay, now here, clearly the rectangles, and again, there's supposed to be infinitely many rectangles, but the rectangles under approximate the area, yeah? Okay, and so what follows? Well, I just said this, and now we can see that the area given by the rectangles is this, and so then we could write it succinctly like that, and that you're familiar with from the first part, and of course then we could write this instead, right? This here, which is this here, could correspond directly to this, right? Okay. And where to from here? Well, this time, as we said, since the sum of the areas of the infinitely many rectangles under approximates the area under the curve, from 2 on, we can say that the exact area is bigger than the sum of the areas of the rectangles, right? Okay. And since this time we're assuming that the integral converges, if the integral, this here, is convergent, then what follows? Well, since we said that f of x is greater than 0, the following has to follow, which is that the integral from 1 to n of f of x dx is less than the integral from 1 to infinity of f of x dx. Clearly, if we add on more x's, right, if we cover more x's, then like we're going to get something bigger, since we said f of x is greater than 0. That is, we said f of x is positive from the get-go. Okay, and then from here, it should follow that we could write this, right? Clearly, the exact area, which is this, is bigger than the sum of the areas of the rectangle. So there's nothing new here. And we've already showed this in the earlier step. So we could do this. All right, where to from here? Well, since we want our series to start at 1, what we could do is, in this inequality that's 3 parts, we can, in each part, throw on a1, right? We're adding the same thing to each of them. That way, we can have our series start at 1 here. Yeah? Okay. Cool. And where to from here? How about here? Well, if we say that a1 plus the integral from 1 to infinity of f of x dx, this here, is some number m, since we already said that the integral, this here, converges, then that means that a1 plus this number has got to be some finite number m, right? Okay, so that means that our series is bounded, right? Okay. Not only is our series bounded, we see that the sequence of partial sums, right? And partial sums means, like, if we fix k to be some finite number and then something bigger than it and so on, we see that the sequence, yes, this is a sequence, sorry. The sequence of, I said series, but I misspoke. The sequence of partial sums is bounded. Additionally, we're going to show that the sequence of partial sums is increasing, and this is how we're going to do that, which is, well, if we look at s sub k, so the kth partial sum of our series, then it's got to be strictly less than s sub k plus ak plus 1. So if we add the next term to s sub k, then s sub k has got to be smaller than it. We already said that f of n is positive, and so the a sub n's are also positive. But then this here is equal to this here, which in turn is equal to this here, which will be the k plus first partial sum. So we have from here, my mouse is going everywhere. We have from this inequality that s sub k is less than s sub k plus 1, meaning that the sequence of partial sums is increasing. Okay, now recall the monotone convergence theorem, which says that, like, if you have a bounded increasing or decreasing sequence, then that sequence must be convergent. So from these two things, which is being bounded by m and what I stated here, we see that our sequence of partial sums, these guys, are bounded and increasing. And therefore, voila, by the monotone convergence theorem, the series converges. Yeah? Okay, cool. This completes the proof, and examples 1 and 2 will follow. And if I find like a really interesting problem, then I'll make an example 3. But for now, because I prove that a p series, when p is greater than 1, converges using the integral test, for now, that video could serve as example 3. Like I said, examples 1 and 2 to follow. I hope you enjoyed this video and keep watching. Take care.